Since the birth of our planet, the Sun has been essential to life on Earth. The fundamental reason for our existence within the Milky Way, this star, which is 332 times larger than the Earth, was formed more than 4 billion years ago and contains more than 99% of all the matter in the solar system. More than 150 million kilometers away, this hot ball of glowing gases is the main source of energy in the form of heat and light necessary for all the Earth's processes. Arguably, the most important process is photosynthesis. Light energy from the Sun is converted into the chemical energy required to sustain life. Without the heat of the Sun, the Earth's surface would be about 32 degrees Celsius cooler, and experts estimate that it will begin to cool within 5,000 million years. Until then, it will remain the largest source of electromagnetic radiation in the planetary system, transforming 700 million tons of hydrogen into helium every second. In other words, 5 million tons of matter into energy. As our nearest star, the Sun marks the beginning and end of each day and shapes our seasons and climates. Therefore, it is of little wonder that the Sun has been the object of man's curiosity since time immemorial. In the 17th century, in his quest to unravel the secrets of the universe, Galileo designed and built the first known astronomical telescope. His telescope allowed him to make discoveries such as sunspots, confirm that the Sun rotates and that planets orbit around the Sun, not the Earth. "400 years later, man is still observing the Sun with the same fascination as Galileo. Recent technological advances have been an important step forward for the astronomical engineering sector, offering the astronomical community the opportunity to study the Sun with more precision and rigor than ever before. Successive achievements in the field have led AURA, the Association of Universities for Research in Astronomy, NSF, the National Science Foundation, and the NSO, the National Solar Observatory, to launch the DKIST project, the world's largest solar telescope. These are the same organizations that in 2010 put their faith in IDOM to design, manufacture and assemble the dome of the telescope. This project has been implemented by IDOM ADA, the Advanced Design and Analysis Department of IDOM. IDOM ADA is responsible for leading some of the most challenging and innovative projects of the firm, using cutting-edge technological innovation in the development of structures, mechanisms, and control systems.
IDOM is developing a significant activity in the astronomy field. It has designed and been engaged on the fabrication on some of the largest, more complex enclosures in the world, the Quixote CMB project telescope and telescope systems for large telescopes such as the folded cassegrain instrument rotator for the Gran Telescopio Canarias on La Palma.
We have a large experience in manufacturing and fabricating capabilities all around the world. Everything from industrial projects through scientific and testing projects. Everything from football stadiums to oil refineries. And telescope projects and astronomy projects are similar in complexion and have a lot of challenges for on-site work.
The DKIST enclosure was a very attractive opportunity for us, a real challenge that we wanted to take. IDOM supplies the DKIST dome as a full manufactured and commissioned part turnkey. We do not just supply engineering, we supply the whole manufactured part. In close collaboration with our office in the US, It has been a very effective collaboration.
This structural masterpiece, with which the Sun can be observed as never before imagined, will be installed in the archipelago of Hawaii in 2016, specifically at the Haleakala volcano on the island of Maui at over 3,000 meters above sea level. From there, highly qualified astronomers can study and anticipate the behavior and variations of our nearest star, which directly affects our climate. The same star we are analyzing to understand the processes of fusion that we are now trying to replicate as a source of alternative energy on our planet, and whose solar storms interfere in our electrical and electronic systems. However, although it is being installed in the middle of the Pacific Ocean, the design, manufacture and pre-assembly of the dome has been carried out on the other side of the world, on the outskirts of Bilbao, in the Basque Country, near the headquarters of IDOM.
Building the largest solar telescope on Earth is a challenge by its own. But if we take into account that it's going to be assembled in Maui, on a remote island, the challenge is even bigger. It's located on a national park, so it has a lot of restrictions related to the environment. It's located on an island which doesn't have industrial power. The cost of fabricating, transporting and doing the assembly there are high. So any issue that could appear at the site, it will have been a real problem.
We explored the options of fabricating this all over the world. We initially thought of fabricating on this in the US directly. Finally, we also analyzed the possibility of manufacturing this in Bilbao, close to our headquarters, and we found it was the most cost-competitive solution. So that's the reason why we opted for this solution.
We have here a large number of industries that provide high technology solutions at a very competitive price.
Truly, the fabrication quality and capacity of the Basque region was outstanding, and it was a lucky coincidence that that kind of fabrication resource was also within easy driving distance to our headquarters in Bilbao.
With that, what we try to achieve is to perform the assembly in an area where we have a really close access to equipment, to a crew for adjusting parts, machining, in order to be able to solve any problem that we could find out during the assembly.
In 2010, a team of highly qualified IDOM professionals began planning what was to be our most innovative engineering project. A complex task that involved close collaboration with our client. An extremely high level of coordination between the teams involved in different parts of the world, such as Germany and the United States, was also essential.
AEC and IDOM have great experience in providing feasibility studies in all types of projects. One of our values that we provide clients in the astronomy sector is to be our ability to work on all phases of the project. Everything from preliminary feasibility type studies all the way through detailed design, fabrication, and then construction phase services. One of the primary challenges on this type of project is to convince the customer of our ability to work in a multi-office environment. Those challenges can be overcome with great communication, where we've got a customer located in one section of the world, the project's going to be delivered in another section, and we've got design offices in the United States and Spain, and we're all collaborating on the same project.
This means that we try to build a very close working team together with our client. It's part of our philosophy.
Hundreds of specialists have worked hard for 4 years to bring the dome to life. 27 meters in diameter and 22 meters high, covering the heart of DKIST. Equivalent to a 7-story building and weighing 500 tons, the enclosure will move with millimetrical precision, allowing the 4-meter primary mirror to observe the path of the Sun throughout the day.
IDOM has designed a DKIST enclosure, which is the rotating building that protects the telescope when it is not in operation, and that positions the entrance aperture stop during the observation, making sure that only the primary mirror is evenly illuminated.
This enclosure is a perfect example of a system of systems. The role of the system engineer is to maintain the coherence and to flow down all the requirements between or among a lot of different subsystems.
As mechanisms, structure, cladding, all sorts of installations, so you need a very well organized and integrated engineering team to deal with the design and then to deal with the manufacturing and commissioning of the projects.
From the beginning of the design phase, the complexity of the structure has been a real technological challenge. Its great dome would have to move with an accuracy better than any other telescope dome. An even greater challenge when we consider that the design of precision systems are the Achilles heel in the construction of this type of rotating building.
To move such large pieces of steel in a very precise and smooth manner is a problem that's been attempted by many telescopes and not always achieved.
Usually, telescope domes are mechanisms that only need to be moving in a discrete way, performing large movements to correct the position of the aperture of the telescope, and are systems whose reliability is far from ideal.
The dome consists of two fundamental systems that allow the Sun's position to be precisely tracked. The first is the shutter system, which positions the opening of the telescope in elevation and contains the mechanism that opens and closes the aperture cover, allowing sunlight to shine on the primary mirror of the telescope, while protecting it when not in use. The second azimuth system permits the large dome to rotate using 10 bogies. The system is equipped with a total of 8 gear motors and 18 steel wheels. A new system was needed for the DKIST, more precise, durable and reliable than any other telescope, to correctly move the shutter system, whose main structure weighs 30 tons.
The mechanism that moves the aperture in elevation is a shutter mechanism similar to that of other telescopes, but it has been specifically designed to avoid the problems on other similar structures, and it is driven by means of a crawler mechanism, which is an innovative mechanism designed and patented by IDOM in order to be able to move large structures in an efficient, reliable and an accurate way.
The crawler mechanism consists of a system of 6-toothed cones. The special configuration, driven by motors, would smoothly move the structure. Thanks to the multiplying effect, the two units integrated into the dome have the power to move the 30 tons of the central structure and the counterweight system. A mechanism capable of moving large structures with a level of efficiency and precision unknown until now.
The crawler unit concept is something that has been in the department for a long time. A new patented mechanism that was designed by our department and that we decided to perform some early tests on a prototype unit in advance in order to assure during several life cycles of the mechanism that the tolerances, the durability of the mechanism was the one that we were targeting.
The tests carried out on the preliminary prototype proved a success. The team had engineered a mechanism that would help them overcome the most important challenge of the workings of the dome. All that remained was to design a suit for the Great Dome, the second lateral structure and the cladding system. The secondary lateral structure was designed as a steel skeleton consisting of 10 large vertical trusses and 6 horizontal trusses. Between these, hundreds of crossbeams would complete the framework to give the DKIST the necessary strength to withstand major earthquakes in one of the areas of the planet most affected by seismic activity and exposed to hurricanes at speeds of over 300 kilometers per hour. The 250 white modules of the facade cover the dome, isolating the interior of the telescope from the effects of rain, snow, wind and solar radiation. Thanks to the highly refractive paint, modern integrated cooling system and a system of more than 100 windows for ventilation, the effect of solar radiation on the surface of the dome is eliminated, and the inner temperature of the DKIST is perfectly balanced with the outer temperature, a key achievement that will prevent image degradation in this precise solar telescope. After completing the design of the secondary structure and the modular cladding system, manufacturing and assembly phases commenced. The two stages were developed almost in parallel and allowed engineers to perform the factory assembly and test phase, make all necessary adjustments to the various components of the dome, comply with all the requirements of accuracy specified during the design phase. During this phase, the assembly process itself was also tested. Since the process would have to be repeated in Hawaii, nothing could go wrong. Essential training that would serve to simplify the final erection process on a challenging site. The litmus test began in February 2013 with the task of site conditioning, making a replica of the interface between the building and the ground on which the dome would finally be installed. A surface on which the technical team installed a track composed of 15 segments on which the bogies would later move the azimuth system.
After performing the assembly of the rail, we assembled the main framework. The main framework is composed by a base ring, which are 14 segments around 10-15 metric tons, and two arc girders where the shattered tracks are assembled, also like 9 segments each.
Installation of both the main base and the two parallel arches was one of the most complex assembly operations. Each of the arcs has a track on which the shutter system moves back and forth, driven by the crawler mechanism. Two major elements that will determine the path of the eye of the telescope to track the orbit of the Sun. Smooth and precise movement incorporated in an infrastructure whose assembly was carried out to a margin of error of millimeters.
The assembly that was performed at ground level, we achieved really tight tolerances under the millimeter. And after the assembly on the base rings, we were able to achieve tolerances under 2 millimeters, which for a large structure of 20 meters diameter, it was an amazing achievement.
Supported on temporary supports to avoid undue forces that could damage the azimuth bogies, the skeleton of the dome gradually took shape. Meanwhile, not far away, members of the IDOM team were finalizing the assembly of the components of the crawler, a delicate and patient assembly job that resulted in the star piece, the most innovative part of the Great Dome. Once all the pieces had been assembled, the crawler was subjected to several operational tests. It was confirmed that the dome far exceeded the desired requirements for durability, accuracy, and reliability. A successful process that also served to help make this mechanism an even more perfect machine.
That early unit was tested replicating a life of more than 10 years. And in that process, we were able to learn and to do a value engineering of that mechanism in order to improve it for the final and best performance of the enclosure.
With the crawler fine-tuned and the trusses of the secondary structure recently manufactured, the time had come to install the internal frame of the dome, an interlaced steel structure whose joints are the key to distributing the weights and forces that the telescope will be exerted to during its motion. Although it may look like the steel structure of a conventional building, it has in fact been created as a high-precision living element. This is why it's been designed and built as if it were a machine. With the frame completed, it was time to install the structure of the shutter system. 3 large 7-meter wide sheets, the largest of which weighing 30 tons, and 2 smaller sheets 7 tons. Driven by the power of the crawler, it will determine the altitude positioning of the eye of the telescope. Precision installation on the guide rails of the arches would not be an easy task, even more so under adverse weather conditions.
They were the largest pieces to assemble. Although they are not heavy structures, it was a critical process during the assembly because with little wind, those structures could really move. And it was one of the challenges in order to be able to place them right between the air girders on the shutter tracks.
During the factory assembly, we've been facing several challenges, and one of that has been the weather. Times in which we've been working with rain, with high winds, and so on in conditions that were difficult. And this has only been possible with a team that was significantly involved and was able to bear all these conditions in order to make sure that project was properly achieved and completed.
Following this, the team from IDOM proceeded with the installation of a simplified version of the azimuth and altitude cable wrap. In other words, the system which provides electrical power, cooling water and control communications to the moving mechanisms. Given its large size, assembly and testing of the final azimuth cable wrap were carried out in Germany at the manufacturer's facilities. This rotator unit is more than 20 meters in diameter, the largest ever installed on a telescope. Therefore, it had to be tested separately. The design and state-of-the-art equipment means that a force of less than 100 kilos is needed to move the 10 tons it weighs. An extremely smooth movement designed to prevent any disturbance that may affect the correct operation of the telescope. Once the electrical installations were connected, it was time to activate the large dome to check that the tracking and synchronization movements between the two systems met expectations.
Synchronize the tracking means synchronize azimuth and altitude movements. So it means synchronizing rotating of 500 tons of steel against moving up and down 50 tons of a shutter. The challenging points were to synchronize azimuth and altitude and to be speaking with the overall telescope control system. It was really challenging from the control point of view, and it's really incredible the accuracy that we have got with such a big structure.
After verifying that both the azimuth and the shutter system mechanisms were working properly, the engineers from IDOM lowered the dome into place on all 10 bogies. A complex operation which required 4 hydraulic jacks with a load capacity of 400 tons each. With the 360-degree rotation at 100% speed capacity, the behavior of the control system and the operation of safety systems were checked before making the final adjustments.
Taking in account you are mixing the torque of 8 bogies and 2 shutter mechanisms. The drive and control system is challenging. One of the challenging systems of the telescope is based on a distributed control system, the control loops. Sharing the total torque among all the bogies, how you share the torque and how you achieve these strict pointing requirements was a key aspect of this, and we have developed very, very good control loops.
While the rear door to the dome was being installed and the opening and closing mechanism and the TEOA platform were being completed, the giant puzzle was put together and the dome was given its color and definitive shape, a design that will make maintenance of the telescope mirrors much easier. With all parts and mechanisms integrated into the structure, the team from IDOM submitted the dome to its final test. In March 2014, the engineers put all the motion control systems into operation at different speeds. It was the moment of truth, the moment when the great dome, 22 meters high and 27 in diameter, would have to move its 500 tons smoothly and with millimetrical accuracy. After a few moments of great elation, the engineering team confirmed the success of the tests carried out during manufacturing. With an almost imperceptible movement, the dome rotated smoothly at 0.004 degrees per second, far from the 2 degrees per second maximum speed that the motor of the dome is capable of reaching. A slow and difficult operational speed, but necessary to track the position of the Sun accurately. The requirements set during the design phases were more than surpassed, and the main mechanisms responded positively, well above initial expectations. This dome would move more smoothly and with greater stability than any other dome built so far.
Performing a factory assembly has a lot of advantages. The main advantage is that we have been able to test all the mechanisms and check the performance of the complete enclosure. We have been also able to perform most of the parts of the fabrication during the assembly in a way that all the parts have been exactly adapted to the real position of elements. And the last main advantage of this factory assembly has been that we have been able to test the assembly procedures using the same equipment, the same limitations that we have at the site in order to replicate exactly the same procedure that we expect to do in the mountain.
After 4 years of hard work and dedication, the IDOM ADA professionals looked up to watch the movements of the dome of the world's largest solar telescope, knowing that they had just finished something that would go down in the history of astronomy. The perfect finale to a unique project, the success of which was a reflection of the high commitment of all the engineers.
One of the things that I'm most proud about of this project is the way that we've addressed all the technical challenges and maintained a great customer relationship. Our team made the project more than just a job. Challenges and questions have come up on this project all hours of the day, and our team has been able to think of this as more than just work, but it's really a passion to IDOM and AEC. This is our whole philosophy: to maintain the client relationship is a must.
A number of the project team members are amateur astronomers that has been engaged on this project. An extra component of passion, I would say.
Everybody in the whole team must be highly motivated in this project. Our engineers, our collaborators, our suppliers, our client, that must be fully integrated in the team.
As a system engineer, has been really a pleasure just coordinating such a big and such a fantastic team.
I really think it's the dream of any engineer, to be able to be involved in such a unique project that it's going to mark the history of the sun science, and also to be involved in all the different phases of the project. I feel fortunate of having been able of working together with such a great team, to have the opportunity of working close by to all different expert and qualified persons of different fields in engineering that have made this dream come a reality.
As it should have done, IDOM opened the doors of the dome in the company of its clients, collaborators and local authorities with an inaugural ceremony to mark this milestone of modern engineering.
The farewell ceremony was a happy day. Somehow all this joy from our side It meant celebrating that we had been able, after so many years of hard work, to supply, to design, to manufacture, to commission what is the world's largest solar telescope.
This was the grand farewell before disassembling all the work carried out and packing the dome into 60 containers that would leave from the port of Bilbao towards the archipelago of Hawaii. The different parts and pre-assembled dome mechanisms will travel thousands of kilometers to the island of Maui, where the DKIST will be installed at 3,000 meters above sea level. The same sun that the world's most important astronomers will observe through the world's largest solar telescope, with a sharpness and definition unknown until now. Constantly gathering information about its behavior, allowing us to unravel its greatest secrets and improve our relationship with the main source of life. All of which is a giant leap forward for researchers in the observation of our solar system, allowing us to take over the baton from Galileo and study the great unknowns of the Sun with the most advanced technologies of our time.